Hello friends, welcome to CEC live lectures. Dear friends, today in this session we are going to continue in our series on cloud computing. We are going to talk on cloud file system, under which we are going to discuss Google file system and the big table. For the discussion on the topic, we have with us in our studios Dr. Kashish Ara Shakil. Dr. Kashish Ara Shakil is an assistant professor in Department of Computer Science and Engineering, Jamia Hamdard. Friends, let's welcome our guest Dr. Kashish Ara Shakil, and let's try to have in-depth knowledge on the topic, that is Google file system, as well as on the big table. Hello ma'am, welcome to the lecture.
Hi. Hello dear listeners, I am Dr. Kashish Ara Shakil, and today we will be studying about what cloud file system is, and in particular we will be stressing upon Google file system and big table. In the last lecture we had discussed about what kind of data is prevalent in cloud, what are the sources of these data, and we had studied that this kind of data is of huge variety, it has huge volume, it is enormous. And the traditional systems, they do not handle such kind of data. They fail to handle such kinds of data. Therefore, what we need is a specialized system for handling these kind of data. So, what are these kinds of systems? We will be discussing in today's lecture and the next lecture. In today's lecture, we will be particularly stressing upon Google file system and big table. So, before beginning with cloud file system, let's have an overview of file system. What basically a file system is. A file system is basically a system that permanently stores a data. So it is a system where you can store a data, and to store these data you need to have something called files on your disk and your media. So all the data which you are storing, it will be stored in forms of file, and all these files are managed by the operating system. So what basically now a file system is? It is basically a mechanism through which you can store data in your system. So the part of operating system that deals with these kind of files is known as a file system. A file is basically, it is nothing but it is a collection of disk blocks, and the file system, it maps the file names and the offsets to the disk blocks. So it is basically a file system is a storage mechanism of files on your system. So how the files are particularly stored in relation to cloud, and how does a cloud file system looks like, this is what we are going to discuss. So a cloud file system may be a file system which comprises of a hub and spoke kind of network model. So in cloud computing, basically the cloud service providers, as we have already discussed, they are nothing but these are the entities who are going to provide you computing services. So in case of cloud computing, the hub, the center of this model will be the cloud service providers. So there are different kinds of cloud service provider. For example, we have public cloud service providers like Amazon, then we have Microsoft, Azure, then we have Google Cloud. All these, they form the hub part of the model. And apart from the hub, we have spokes area. So what are these spoke areas? They basically comprise of the data centers, then the branch offices, the remote locations from which the users are accessing the cloud services. So a cloud file system, it basically looks like a hub and a spoke model, with the hub as your cloud service providers and the spoke in form of the data centers and the clients who are accessing these services from different geographical locations. So basically in cloud, what is happening is all the data centers, all the clients, they are located at different geographical locations. So the file system basically being used in cloud is a kind of distributed file system where all your files will be distributed on multiple clients on multiple machines, and It will be spread over multiple autonomous computers, and it is not necessary that these computers are located at the same geographical locations. They can be in different geographical locations as well. So what a distributed file system should provide? It should provide network transparency. That is, it should hide where the data and the file is actually located. So it should provide network transparency, and it should ensure high availability. So it might be, sometime it might happen that some of the clients, they can be accessing resources at say 2 a.m. from a data center which is located in India. So at this point of time also your system must be available, your cloud file system should be available, and even if it is like 10 a.m. in the morning, then also it should be available. So it should provide high availability at all times, and it should be available even in case of a crash or say some kind of natural calamity if it has occurred. In that case also there should be high availability of the cloud file system. So it should ensure that the data is available at all times, irrespective of what the condition is, what the climatic condition is, what the geographical location is, and whatever the time is. So the data in a file, distributed file system, it should be available at all times, and it should be transparent, because for me as a user, I should not be aware which data center I am accessing. If I am sitting in India, I should not be aware whether I am accessing my file from a data center which is located in India or from a data center which is located in USA. So this is the figure which depicts what a distributed file system looks like. A distributed file system, it basically consists of a centralized communication network, and there are different clients which are accessing these services. These clients are also distributed at different geographical locations, and then we have servers. These servers are also distributed at different geographical locations, and at the back end we have data centers which are again distributed. So in a distributed file system there is no centralized thing. Everything, all these servers, they are distributed, all the clients, they are distributed. So this is what a distributed file system looks like. Since we talked about distributed file system and then we talked about cloud file system. So how does a distributed file system for a cloud looks like? A distributed file system for a cloud is a file system that permits many clients to access the data, and it not only the data, to access the different services, to access the different platforms which are being provided. All the platforms, all the operations, they should be accessed by the distributed file system at all time. And in case of a distributed file system for a cloud, every record would be divided into many elements called chunks. So all the files, they are not stored in one data center at a time. The files, they are not stored in one particular location. The files, they are divided into subparts, into smaller parts called as chunks, and then they are stored. Then typically knowledge in these files, they are stored in a hierarchical manner. So what do we mean by a hierarchical manner in this case is, for example, if you're storing any file, any say normal file in your system, how do you store it? You create a folder for it, or even if you're not creating a folder, there will be some default folder under which your file is getting stored. So it is a tree-like structure that the folder will be the topmost in the hierarchy, then there will be some subfolder, and then your file wherever it is stored. So the knowledge or the file in a distributed file system is stored in a hierarchical manner. And their area unit, they may provide many ways to share the files. So there is no just a single way to access these files. You can either access through the client API which is being provided to you, or maybe through any other UI interface which is being provided by the service providers. And even as a client, you might have different views of the same file system depending upon the kind of permissions you have to access those files. So this is how a distributed file system looks like. And apart from this, Since the data, your file, is stored in some remote server, therefore security of your file is also being taken care of by the cloud service provider. You as a client, you do not have to worry about the safety of your file system wherever your file is being stored. And these files which are being provided by the cloud file system, it should be highly available, it should be confidential, and the integrity of the file system should be maintained at all times. So a cloud file system should be distributed, it should ensure high availability, it should ensure that the knowledge is organized in forms of chunks of data, and these chunks, they are highly available, and for you as a user, these things are highly transparent. You are not aware what is going on in the back end. So what is a distributed file system architecture? How does the architecture for a distributed file system looks like? So basically, in case of a distributed file system, we have a client server kind of model. So the resources and the sources from which you will be accessing your files, these sources are generally called as the servers, and the interface from which you are accessing, that will be called as a client. So in general, one server can act as a client for another server, or vice versa. So what we have in a distributed file system architecture, we have a kind of client server model where there can be many servers catering to a single client or multiple clients, or a client acting as a server for another client. Usually what we have is, we have a very clear distribution between the two. There is a clear distinguishing that which of the computers will be treated as a server and which will be treated as a client, because generally the servers, they will be having a higher configuration. Higher configuration can be in terms of RAM, in terms of memory, and in terms of other resources which are being provided. And a client is generally a kind of dumb terminal through which you will be accessing these services. So this is how an architecture for distributed file system looks like. Similarly, in this diagram, we can see that there can be multiple servers, and there will be a computer network through which these clients will be accessing the servers. So this is what was the general look and feel of how a cloud file system should be. It should be a distributed file system. It should divide the files into multiple chunks. It should be highly available at all time, and it should be highly reliable. It should be secure, and apart from this, it should be available at all times. So this was the kind of cloud file system that we need. But what kind of data we are going to store in these file systems? Let's have a look at this. So in cloud computing, basically the data, as we had already learned in the last lecture, the data in cloud is generally very big. It comes in a lot of variety. It has a very high veracity. It has a huge volume. So this kind of data of massive volume, it needs to be stored, and this kind of data is referred to as big data, because this data is enormous, and therefore its storage is also quite challenging, because the data, it is massive, and we need systems that can scale up. What do we mean by scalability? By scalability, we mean that our servers should be able to store, say, data in GBs as well as data in petabytes also. So our systems should be designed in such a manner that it should handle data of any volume, and our storage, whatever we are going to store, should handle all kinds of failures also. If there is a network failure, if there is a disk failure, all these things should also be handled by the system. And we say that in case we are going to use distributed file systems, so what we mean is we'll be using multiple machines. So our system should be designed in such a manner that these machines should be highly available and our system should be free from any kind of crashes, any kinds of failures of these machines too. So how are we going to then store this massive, huge amount of data? So one of the approaches which is being used and can be used is we just divide the data into multiple chunks, and then we can, if we are going to process this data, we'll be processing them into on different nodes, and then we'll be combining the results. So big data processing can be done if we are doing this in a parallel manner. What do we mean by parallel? That we are executing it in form of chunks at the same point of time. So what will be the advantage of this? If we are going for a parallel technique, then the advantage of this approach will be that it will be a very fast approach because we are saving on the time, our resources will be utilized in an efficient manner, and one more thing is we can make use of commodity hardware which is available with us. We do not need to buy a new infrastructure to handle such kinds of data. So distributed system, it works well with clouds because what we can do is we can just distribute our work onto multiple commodity machines. So distributed processing is also non-trivial because if we are going for distributed processing, we need to know that how are we going to synchronize the task, because the task will be carried out by multiple machines, and so how the task will be synchronized, that is a problem. And what is going to happen if one task fails, because there will be multiple tasks which will be executing a particular process. So what is going to happen if just a single task fail? Will all the tasks continue to run, or the entire program will halt? So this is something which we need to take care of. Then apart from this, how the workers, how are the different machines, they are going to exchange the results. Is one machine storing some kind of crucial data which should not be available to other machines, or should it be available? So this is something which we need to think about if you are going for distributed processing of data. Then how the tasks will be synchronized and how the tasks will be allocated. Will they be allocated on the basis of the size of the file? Will they be allocated on the kind of the task? What is the allocation criteria? So this thing should also be taken care of when we are going for distributed processing of data in cloud. So we talked about how the distributed processing is going to take place, but what we also need to take care of, what data is going to be stored, because big data is just nothing, but it's massive, it's huge. Do we need to store the entire data, or we need to store some part of it? So what kind of data needs to be stored? So users' data will be in itself, it will form a bulk on the file system content. All apart from the user data, whatever the data the user is generating, do we need to store any other information? Yes, we'll be needing to store the metadata relating to that file. So what the metadata for a file can include? It can include things like who are the users, who are the owners, who all has permission to access these kinds of data. So all this metadata information should also be stored. So information can be on the basis of volume-wide information, like what is the available space, what is the formatting criteria, what all character set we are using, and on the basis of per file, the kind of metadata we can store is who will be the owners, what is the name of the file, how the modification of the data will take place, what is the point of time that last modification was done, whether a user can access this file at a particular time or not. So all this kind of things should also be taken care of when we are storing data. So what are the design considerations which need to take place? Since this data is massive, we need to take care of how the namespace is being done, how the physical mapping is done, how the logical volume looks like. Then we have to also take care of the consistency, whether the data is consistent at all times or not. Yeah, and also if there are multiple users who are accessing the file at one particular time, then how the file access should take place. Whether when one user is reading a file, should another user be allowed to write it? And if one user is writing a file, should another user be allowed to write it? So consistency should be ensured. Then security, how secure your file system is, how you will be rating the authentication of the file systems, what will be the authentication criteria for the files. Me as a user, do I have access to the file or not? Am I authorized to access these files or not? Then another design consideration is reliability. Can files be damaged if there is suddenly a power off, or can files be accessed at any particular time? So all these design considerations should be taken care of. So we talked about what are the different file systems, what a cloud file system looks like, what is a distributed file system, what kind of data should be stored, and what is the data problem with cloud. So on the basis of this, we have different file systems which are being used in cloud at present. One is Google file system, which is being actively used. Then we have Bigtable, which is based on Google file system. Then we have Hadoop distributed file system. Apart from this, we have HBase and Dynamo. In today's lecture, we'll be looking forward to Google file system and Bigtable, what Google file system is and what Bigtable is. In the next lecture, we'll be covering up the next three file systems. So what a Google file system is? What is the motivation for Google to develop its own file system? Because Google file system, as the word suggests, it's a file system which has been specially developed for Google. So why did Google had a need to develop this system? Because the data which is being inputted in Google, it is very large, because there will be billions of pages which are being involved, because Google has massive amount of information. It has information from multiple users, from multiple pages, and of course there are multiple clients also which are hitting Google at per second. So the motivation for developing a separate file system for Google was the volume of data. So why did not Google go for the existing file systems, like we have network file system? It was because network file system, it had many deficiencies in form of network congestion and in single point failure, because in Google there is a lot of network congestion, because millions and billions of users, they are accessing the file at one particular point of time. So network file system, it failed to handle such kind of request. And of course, Google, the kind of problems which Google faces is very different from what you and me face every day to day. Google file system was basically developed and designed for Google apps and the kind of workloads which Google handle. It's basically demonstrate how large-scale processing can be done on commodity hardware. So what a commodity hardware is basically nothing but the available infrastructure which we have. So GFS, that is Google file system, it basically demonstrate how you can support large-scale processing with the existing infrastructure which you have at your hand. And it is also designed to tolerate frequent component failures, because since Google, it is catering to millions of users, they will be hitting on with Google with all sort of queries. There can be some malicious users who might be hitting Google for their resources, for stealing of certain information. So it should be free from all these kind of failures, all these kinds of attack. So it was designed in such a manner so that it could handle such kind of failures. And it was optimized for huge files, and these files are either appended or they are read. So whenever you are, basically Google is nothing, it's a search engine. So whenever you are searching something on Google, what you're doing is you're performing a read operation. So it was developed to perform read on your files in an optimized manner, and of course then it was simple for Google to develop its own file system. It was basically, when it was developed by a team led by 3 scientists, Sanjay Ghemawat, Howard and Shuntak Leung of Google in 2002 and 2003. It basically provides high fault tolerance because it serves large number of clients at one particular point of time. And apart from this, it also serves millions and large number of clients, and apart from serving, it should also give a high performance because it's a competition. It's a very competitive market. Apart from Google, there are other search engines which are coming up like Bing. So what Google should do, it should be able to produce these results in a fraction of seconds. The performance of the Google file system should be high. And Google is also beyond searching. It's not just, now Google is not just a search engine, it is beyond searching. And Google storage is also something which is very important, because Google, it provides Google Drives. So what users are doing, they are storing their enormous information in these drives, and there can be more than 15,000 of commodity hardwares which are handling this kind of information. And apart from this, there are different kinds of exceptions which Google has to handle, and Google also has to handle specific challenges of distributed file system. So friends, we'll be continuing with Google file system in the next half of the lecture. We'll just halt for a short break.
Thank you, ma'am. Thank you so very much for giving us this session. Friends, there is a lot more for you. You're requested to be with us. So we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on cloud file system. In our previous session we discussed on Google file system, and as we promised that we would be talking more on Google file system as well as on big table. So here we are, friends, for this discussion on the topic. We have with us in our studios Dr. Kashish Ara Shakil. Dr. Kashish Ara Shakil is Assistant Professor in Department of Computer Science and Engineering, Jamia Hamdard. So let's welcome our guest, Dr. Kashish Ara Shakil, once again. Hello ma'am, welcome to the session.
So we just discussed about what Google file system is all about. So now let's look at the architecture of Google file system. Basically, Google file system, it consists of a cluster of machines where there is a single master and there are multiple chunk servers. So basically what Google file system consists of, there will be a client which will be hitting for request to the master, and then there will be a chunk server for which basically a chunk server is responsible for all the read and write requests. All the read and write requests are done through the chunk server, and all the metadata regarding any client is stored at the master node. or the master part of the Google file system. So the metadata, it can contain information about the name of the client, the timestamp at which the client accessed the file system, and other things like the size of the file which the client is requesting, etc. So basically what a chunk is basically, it is similar to the concept of blocks in file system. So what it is doing is, it is going to store a certain amount of files. So for example, it can store up to 64 MB of file as compared to a file system. If you are thinking in terms of file system, it can store 64 MB of data. So the problem in this chunk size is for developing a hotspot. The property of chunk is that the chunks are stored in chunk servers. They are stored in form of chunk files. And then we have the metadata. Metadata basically contains information about the kind of files which are being stored. It has basically three types of metadata which are stored. Majorly, one is the file, then is the namespace of the chunk, and the third is how the mapping of the files will be carried out with the chunks, and the location of each of the chunks replicas. So how does the chunk replica comes into picture here is that the chunk replicas basically ensures high availability, so that in case there is a failure of a single node, our system would still continue to run. So this is what we mean by maintenance of chunk replicas. Then metadata is stored in memory, and master operations are basically very fast. And what a master is basically a single process which runs on a separate machine, and it will store all the metadata. So the role of the master part of the Google file system is just to store the metadata. Then the clients, they will not contact the master for any read and write operation. It will only contact the master to get metadata info about the chunk servers which it is accessing. So let's see how a read algorithm takes place in Google file system. If you're operating for a read operation, then how does it take place? So firstly, any kind of application will make a read request. So an application can be me as a user. I can just say that, okay, I want this kind of data to be read from the Google file system. So in this case, this would be the application, or maybe we can have some automated application which will act as a client, and it will issue a read command to the chunk server. So firstly, an application originates the read request. Then the Google file system client, it will translate the request form. It will convert the file name and the range of the file which it needs to access into file name and the chunk index, that is the location in the chunk server where the chunk of the file will be present. And then it sends all this information to the master. So because why it is sending this information to the master? Because master is the one which is responsible for handling the metadata information. The master data, what master will do is, it will respond with a chunk handle, and apart from the chunk handle, it will also respond with the location of the replicas. So if the chunk at a particular location fails, it will automatically be able to replace it with the replica part of the chunk. So client, it picks the location on the chunk server that, okay, I want to read the file from this location, and it will send the request to the location that, okay, read this and this file from this location on the chunk server. The chunk server will respond on the requested data to the client that, okay, this is the data that you had requested for, and the client will forward the data to the application. So how a read operation is taking place here is that any application, it will just issue some kind of command. In this case, it is read. It will issue a read command to the GFS client. The GFS client will ask the master data about the information of the chunk file, that where the chunk file is getting stored, and after this information is returned, it will contain the information about the chunk file as well as the information about the chunk replica where it is present. And once this is returned, what it will do is it will just access the file wherever it wants, whichever file it wants, it is accessed, and then this is returned back to the application by the Google File System client. So what is going to take place in case a system or a user issues a write algorithm? So in this case also, the write request will be issued by the application itself. So once a write request is issued, the GFS client, like in the read operation, it will also convert the file name and the data into the file name and the chunk index, that is location on the chunk server where the chunk will be present, and then it will be sending these information to the master. The master, as we have already learned, that the master, it has the metadata information. So the master will respond with the chunk handle, but now in this case it will have information about the primary as well as the secondary replica locations of the chunk. So, and then the client will push write data to all the locations. So the write on the data is not going to take place at just one location, because the data is replicated across multiple servers, across the multiple machines, or in this case what we are calling these multiple locations, we are calling them as chunks. So this write operation will take place on all the replicas of the chunk, and data is then stored in the chunk server's internal buffer. So this is how a write request is taking place. How? First, an application, it issues a write request to the GFS client. The GFS client, it calls on the metadata that I want to read such and such chunk, and then the master, what it returns the location of the chunk index, the location where the chunk is found, and apart from this, it will also give you the location of the primary and secondary replica positions of the chunk as well. And then what you will do is you will perform a write operation again through the GFS client, and this write operation is not going to take place on a single machine, on a single chunk. It is going to take place on all the replicas to ensure that the data is consistent. And then data is stored in the internal buffers of the chunk servers, and then it is later on stored permanently in the chunk itself. Then the client, it will also send write commands to the primary one, to the primary file. The primary one will determine the serial order for the data instance, and it will write the instance in order to the chunk. Then all the primary will be sending the serial order to the secondaries and will be telling them that okay, you have to perform the write operations. And then the secondary ones will also respond to the primary, and the primary will respond back to the client. So what we got here is that if we are writing the files to the chunk servers, this writing will take place in form of writing on all the replicas. First, it will go to the primary chunk. The primary chunk will issue read requests and it will send it to the secondary chunk. It is written on the secondary chunk, and then it is sent back to the primary chunk, and then to the GFS client, and ultimately to the application. So a write operation will then be performed on all the replicas of the client. Next important thing to ensure in GFS is how the garbage collection is taking place. So what is garbage collection used for? Garbage collection is basically used for freeing your system of any unused memory, so that your system does not have any redundant or unwanted data and there is no wastage of memory. Why we are taking care of garbage collection in Google file system is because Google, it already has to deal with enormous huge volumes of data, and if we are piling up on the garbage data too, it will add on to the volume of the data, and you will use resources unnecessarily. So in order to handle that, we have the provision for garbage collection in Google file system. So garbage collection should take place at both the file levels as well as the chunk levels. If any of the application it is deleting some portion of the files, this should be logged by the master, and it should be, then of course it will be communicated to the chunk server also that so and so file has been deleted. So all the deletion, all the operations should also be logged with the master node. And even if a file is getting renamed, in that case also garbage collection should be ensured. The file can be read under, it can be read under new, or it can be read under some special name, and can be undeleted too if we are just going to rename a file. And if we are deleting any kind of file, any kind of metadata associated with it should also be deleted. So because since there will be multiples, billions and trillions of files, so if we are even storing their metadata, then also it will add to some volume. So if we are deleting any file, we should ensure that the metadata corresponding to it should also be erased completely. And apart from this, what the quality of GFS should be is it should ensure high availability at all times. Why it should be highly available? Because since Google, it deals with multiple of clients, and of course it's a commercial thing, so it should be highly available. This is ensured through fast recovery. If there is a failure at one node, it is fastly recovered. And there should be master replication, chunk replication. Then data integrity should be ensured at all times in form of different chunks which are available. And these chunks, they are divided into blocks of size 64 KB, around 64 KB. Then what is the advantage of developing a file system like Google? First is it supports large-scale data processing. It provides fault tolerance. It provides tolerance even in case of failure of the chunk servers. And it should deliver high throughput. And it also provides a storage platform for research and development, because earlier if we had, say, traditional systems, whenever we were performing some kind of R&Ds, for example, if we were performing some kind of analytics, whatever results we were getting it on the basis of some portion of the data. We were not getting it on the entire data set. So it provides support for R&D applications also. If a file system is able to handle huge volumes of data, it will automatically improve the research which is being performed. So these were the advantages of Google file system. And what Google file system is, now we'll be moving to the next file system which is being used in cloud, that is Google Bigtable. So why Google Bigtable? So just like we discussed that cloud, it basically comprises of huge volumes of data. Here also we have lots of semi-structured data at Google. Then this data can be in form of URLs which are there for storing different web pages. Then we have contents like crawlers, metadata, we have links, we have anchors, we have information regarding page ranking. So apart from this, there are data about users depending upon the choice, their content, and the kind of queries a user is making, and whatever the search results a user requires. So apart from this, the location of the geographical location of the users is also different. So this also contributes to data for Google. So geographical locations, it can comprise of data which is being accessed if you're sitting in some kind of shop, if you're sitting in some kind of restaurant, or even if you're at your home. And of course, if you are on the road, if you're traveling, that time also you are accessing data at Google. And apart from this, there is data coming from satellite images, then user annotation data, all these, they contribute to loads and loads of data for Google. And for handling these kinds of data, the scale should be very large, because there will be billions of URLs, there will be hundreds and millions of users, and there will be data coming up from satellite images which could be contributed in, say, like more than 1,000 TBs. So why don't we just use any commercial database? Why should Google develop its own database? The reason is that the scale, the kind of applications which Google is handling, it is enormous. It's not something which we use in our everyday life. So a traditional database system, it will just fail to handle such kind of data. And if we were using the traditional ones, what we had to do is, if the demand for data is increasing, we would just have to vertically scale up. We would have to buy in a better server, a better machine to handle such kind of data. So the cost would just go bongs. You'll just go mad handling such kind of costs. So in that case also, Google Files, this big table, it comes as a better option. And you need to optimize the storage even at lower levels. It's not like you have just like billions of records. You can't just go up at the topmost level and try to optimize. You should start optimizing from the least possible level, from the lower levels, and then go up. So you need a separate database, a separate something like big tables. So what are the goals which a big table aims at achieving? One is that it wants asynchronous processes to be continuously updating different pieces of data. There will be different users which will be accessing the data at any particular point of time. They are not synchronized. So this kind of database should be able to handle any kind of synchronized, unsynchronized access. Then it should need to support very high rate of reads and writes, because Google, it handles multiples, millions of operations per second, so it should be able to handle very high read and write requests. And even if you as a user, you are accessing some kind of information, even if you're accessing information, then Google needs to search through trillions of records to just answer your single query. So so your database should be efficient enough to handle such kind of requests. Then you need to have efficient operations like join operations, one-to-one, one-to-many, and any other kind of operations which you need. And you might also want to examine how the data is getting changed in a chronological order, like at what particular point of time this change was brought about. So all these things should be handled. So why should we go for what is basically big table? We said that big table will be a solution for this thing, but what big table is? Big table is a distributed storage system for managing structured data that is designed to scale to petabytes of storage across thousands of commodity servers. So what big table is? It is going to manage huge volumes of data across millions and billions of commodity servers. So what will be the properties of big table? It should be highly scalable because it should handle data of huge, enormous volume. It should be highly available. It should have high performance, and it should be widely applicable. So what big table is? Let's look at it in a more depth. Big table is a compressed, high performance and proprietary data storage system which is built on top of Google file system. So it's just a level up on the Google file system. We just discussed about Google file system. Then we have now a big table which is developed on top of this Google file system. And it also has other features like chubby log service, then SS table, which is an immutable data structure which is being used. Then apart from this, other technologies which are being used by Google is part of Google Big Table. And since we just talked about that, the information in Google should also take care of the chronological order, the order in which the events are taking place. Therefore, timestamp of all the information is also maintained in Google Bigtable. The first public version of this Google Bigtable was developed on May 6, 2015. It was released to the public on May 6, 2015, and it was initially designed to scale to a very large size to handle petabytes of information, and how this information was handled through thousands and millions of servers which are available at Google. And it is currently being used for many Google projects like web indexing, some kind of personalized search, Google Earth, Google Maps, Google Analytics, Google Finance. So for all these things, all these applications of Google, Google Bigtable is being used. It is a kind of distributed multi-level map, and it is highly fault tolerant and persistent. And apart from this, it is highly scalable because it has to cater to thousands of servers at one particular point of time. So it provides high scalability, handles terabytes of data, and handles millions and billions of read and write operations. And it is self-managing too. By the term self-managing, we mean that it should handle any kind of increase and decrease of the request. It is a kind of white column store. And it maps what it basically, we said that it's a kind of white column store, and we also talked about it being a map. So what it is going to map? It is going to map two arbitrary string values. That is, it will be mapping the row and the key value and its timestamp. So we have one more thing here is timestamp, which we already talked about, into an associated arbitrary byte array. Another thing to be noted is that it is not a relational database. In fact, it is a sparse, distributed, multidimensional, sorted map. And the tables in Google file system, which we just talked about, they are optimized by being split into multiple tablets. So all the tables, even in Bigtable, they are being split into multiple tablets, and these segments of the table, they are split along a row. So they are split row-wise in form of tablets of around 200 MB of data in size. And if the tablet size increases, then in that case what they have is they have some kind of compression or algorithms at the back end, such as BMDiff, which handles this. So what are the building blocks of Bigtable? First and foremost, we said that it is built on Google file system. Apart from Google file system, we have a scheduler which takes care of the scheduling of the jobs on the different machines, because again it is distributed, so we need a scheduler. Then we have a log service for being on the distributed log manager. Then we have, for processing of the data, we perform it using MapReduce approach. So GFS, the Google file system, it is being used for storage in form of SSS table file format, then scheduler for scheduling of jobs, log service for master election, location bootstrapping, etc., and MapReduce for performing processing like read and write operations on the Bigtable. So the three major components of Bigtable is, one is we have a library which is linked to every client. Then we have a master server which is responsible for assigning tablets to the tablet server and for garbage collection. And then we have different tablet servers which are going to handle all the read and write requests and for splitting data. If the tablet size increases, then we have clients. Then this is the whole architecture of Bigtable. This is how a typical Bigtable looks like. We have a Bigtable client, and this Bigtable client If it needs to perform any read and write operation, it is going to do it through tablet servers, which are going to handle tablets. So tablet we just talked about, it is nothing but rows of your data. And if any kind of metadata operation is going to be done, that is going to be done through Big Table Master, just like GFS. And then apart from this, we have the only thing extra we have here is we have Chubby, which is a master lock, and which takes care of all the locks of the live servers. So what are the functions which a Google Big Table API provides? It provides support for creation and deletion of tables, then for creation and deletion of column families, for changing metadata, for execution of client, and for performing any kind of row operation, any kind of transactions, and any other kind of processing through MapReduce. The basic features of Big Table is, first and foremost, is it performs high performance. It provides a very high performance alternative than other products which are currently available. It is very fast. And another thing is it is very secure because all the data, it is encrypted. Then it provides very low latency storage because data is utilized in form of low latency storage stacks, and it is fully managed. Apart from this, it provides compatibility with other services like HBase, and of course it provides global availability. So this is it for what Big Table today. In the next lecture, we'll just be studying about how the data model is being done in case of Big Table, and then we will be starting off with the other topics on cloud file system. Thank you so much. I hope it would have been a learning experience for all the listeners. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, you are requested to write to us at info.cec@nic.in if you have any questions or if you wish to give your feedback for this particular lecture or all the other lectures which we have conducted in the past in this series, which are there for you on YouTube. So keep writing us, keep watching us. We will be meeting again very soon. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.